Now, let's talk about neuroscientific basis for neural networks. And some people might ask this simple question: where did this neural network come from? Okay, so think about other machine learning algorithms like a KNN or K-means or mixture of Gaussian. And these algorithms are not from the natures. Actually, we invented. Okay, so we actually created these algorithms based on some logic or some ideas. But neural networks are different. So we have actually working hypotheses. In our brain, we have neurons, and the neural networks are actually inspired by a brain neural networks, biological neural networks. Okay, so long time ago, when neural network didn't work well, then people actually threw this out and they actually used other machine learning algorithms. But still, there were some people like Jeff Hinton and Yoshua Bengio and Yan Kun, and they kept working on the neural networks because they believed that the neural network would work if we have right techniques with enough computational power. So they worked on neural networks even when people actually didn't work because they thought our brain is working based on the neuronal representation. So if we implement this neuronal representation in a computer, then one day it will work. So they were right in a sense. So let's talk a little bit about the neuroscientific basis for the neural networks. Now we know how neurons are working, so we can actually model almost exactly how neurons work. So we have some equations like this, and based on these equations, we can actually model the neurons almost exactly. Okay, and there are some people who actually try to build up artificial intelligence based on this neuronal model. Okay, but this takes a lot of computations. Okay, so to model one neuron, we need the derivative and integral and lots of equations. So to model a really big neuronal system like our brain, it takes too much computational power. Okay, so this is not practical yet. Okay, so instead of having these complicated equations for neurons, then we can actually simplify. So instead of modeling the neuron exactly, then we can actually simplify, okay, so that we can save a lot of computation power. So artificial neural networks are computation models inspired by brain. So this is different. Artificial neural networks are different from biological neural networks, but they were inspired. Okay, so we have nodes and we have weights, but these are doing the same thing as neurons and synapses. And also, we can think of other components of artificial neural networks like ReLU. So the activation function ReLU is actually inspired by neuronal activation in our brain. In our brain, we have lots of neurons and they are connected to other neurons. Okay, so we are getting a lot of information from other neurons, and then the information is represented based on the frequency. Okay, so the intensity is always the same, the amplitude is always the same, and then the amount of information can be represented based on the frequency of the spikes. Okay, then we can gather all the spikes from the neighboring neurons, and then when we sum them up, then if the integral of this information is higher than a threshold, then the neuron will fire. Okay, otherwise, neuron will keep quiet. Okay, it's like ReLU. Okay, so until we have some amount of information, we just keep quiet, and then once the amount of information is above the threshold, then we fire. And also, in our brain, the frequency of the spikes are limited biologically. So even when we have a lot of information from other neurons, but still it cannot fire too many spikes. So there is a biological limit there. So it's like a hyperbolic tangent, right? So if we have a lot of information, but still there is a saturation. So these activation functions are actually inspired by brain neural networks too. So a lot of ideas are inspired by brain neural networks. And when we look at our brain or the animal's brain, then there are two paths. Okay, there are two separate systems. For object recognition or what, then there is a path in these directions. We have eyes here. When we look at some things, then the information goes to the back of our brain, and then this is the first step to process. And then there is a two path, this way or this way. So this way, ventral stream or ventral pathway, we recognize the objects. Okay, we recognize something. And then to dorsal pathway, we actually recognize where or how. Okay, so let's focus on this what path. So we're gonna talk about object recognition. And as I said, when we look at something, then this is the first step, and then we have a second and third and fourth, etc., etc. Okay, there are kind of layers, and when we look at the neural representations on those layers, then we can actually plot these representations in a vector space, right? So actually we can measure this neural representation from monkeys. So we can actually plot these representations in the vector space. This figure explains that. So we measure this neural representation and we plot in the vector space. And then when we actually do this from this layer, then this input image can be represented in this way, and this manifold is really curved. Okay. And as process goes on, then we can take a representation in a layer process step, and then these representations make a flat manifold, which means these representations are more abstract. So when we train the neural network, then we actually observe this kind of phenomena a lot in deep neural networks. So even though deep neural networks are different from the biological neural networks, but they were inspired by biological neural networks, and when we train the neural networks, they have a similar behavior. Okay, that's what I'm saying here. So they work in similar way at least. Now let's talk about the beginning of deep learning. So what was the starting point, and what was the main problem, and how these problems were solved. Okay, so first, it dates back to 1980 when Professor Fukushima actually proposed the neocognitron. So he actually modeled our brain structure with the neocognitron. So he took this idea from the neuroscience and he actually applied some training algorithms back then. But backpropagation was proposed in 1987. Actually, it was proposed in 1970 something, but in 1980, the backpropagation was not popular. So most people didn't know backpropagation. So in 1980, Fukushima proposed this structure with some learning algorithm. And Yano Kun actually took this structure with backpropagation. So in 1989, backpropagation was known to many people. So Yano Kun actually took backpropagation to this structure so that he could propose convolutional neural networks. So that was 1989. So even now, we use CNNs and then, even after this CNN neural network was not that popular because the other machine learning algorithms were better than neural networks because neural network needs a lot of computation power and it needs more fancy techniques to train the network architecture. So people didn't use neural networks. And in 2006, Jeff Hinton and his student wrote a paper in the Science. And in this paper, they actually proposed a deep neural network. And then what is the difference between the shallow learning and the deep learning? Okay, so there are many machine learning algorithms. All the machine learning algorithms before deep learning belong to shallow learning. Okay, So recent advances in AI are attributed to deep learning, as you know. And why deep learning? Why do we have to talk about deep learning while we have a lot of machine learning algorithms? So basically, to understand the complex problems, the model should be powerful enough. So we need a bigger model, okay? But there are two different directions. When we have a neural networks, we can have a bigger network in this direction, so we can have more nodes in this layer, or we can have more layers. So we're going to talk about these two different approaches in the next slide. Anyway, deep networks are expressive and generalizing well. So it has a lot of expression power. So including this MLP, multi-layered perceptron has one or two hidden layers. So including MLP, linear regression and decision trees, all these machine learning algorithms are shallow learning. And from this, if we stack more layers, then we can have a deep neural networks. Here is an interesting question. So decision tree has a lot of kind of seemingly lots of layers. So every layer we have to make a decision like this. But still, this is a shallow learning. Even though we have a lot of layers in decision trees, but it's not deep learning. The main point is the data. Do we actually change the data representation? In deep learning, every layer we actually change the data representation. So let's say this is an input, then at this layer we look at the features directly. And in this layer, we don't look at the features directly, we look at the output of the first layer. And in this layer, we look at the output of this layer. So we actually transform the data representation. But in decision tree, whenever we make a decision, we look at the features directly. The features are not transformed. So even though we have many kind of layers in decision tree, it's not deep, okay? And we can summarize this shallow learning and deep learning with the two factors. First, in shallow learning, feature extraction is done by domain experts. But in deep learning, the features are extracted automatically from data. So we don't need the domain experts. We don't need the domain knowledge. And in shallow learning, we have a separate modules. We need the feature extractor and the trainable classifier. So this feature extractor can be done based on the domain knowledge, or we can actually have another trainable feature extractor like a PCA or something. But anyway, these are separate modules. But in deep learning, we have only one unified model for end-to-end learning. So instead of having the feature extractor and the classifier separately, we have one model. Okay. So this figure summarizes that. In shallow learning, we have a feature extractor based on the domain knowledge, and then we have a classifier. So the problem is this feature extractor and classifier are trained separately. Okay, that is a problem because in deep learning, we have only one neural network, so all the layers are trained toward one direction. But in the shallow learning, feature extractor is trained with different objective function than the classifier's objective function. So there is no guarantee that these feature extractor extract the best features for this classification task. It's separate from the classifier. That's the problem. Okay, then what good comes from deep? So when we make a deep, then what is the benefit instead of having the wide network? So as I said in the previous slide, we can make the model bigger by increasing the number of nodes in the layer, or we can add more layers like this. So we can compare this shallow network and deep network based on this number of parameters. So let's count the number of parameters. In this network, how many parameters do we have? So we have 2 nodes and 8 nodes and 2 nodes. So the number of parameter is 32. Okay, the number of parameter means the number of edges. And how about this one? So we have a 2, 4, 2, 4, 2. So we have 32 parameters. So basically, we have the same number of parameters for both networks. So far, it looks like they have same kind of complexity, model complexity. Then let's check how many paths do we have from x1 to y1. Okay, so in this shallow network, we have just 8 paths. So from this one to this one, there are only 8 paths. But how about this one? From x1 to y1, we have 32 paths, which means deep network can capture more different variations, more different patterns from x1 to y1, which means we can model more complicated relationship between x1 and y1. So that's the beauty of deep networks. Then what about universal approximation theorem? So universal approximation theorem says when we have one hidden layer, then we can approximately model any functions. Then why do we need deep neural networks? So there's another theorem about the advantage of depth. Okay, so some functions represented with k layers may require an exponential size with 2 layers. So as I said in the previous slide, we can have a bigger model with a wide network and deep network. But when we have a wide network, then we need more hidden nodes. When we have more layers, then we can have more kind of variations. We can capture more variations, more patterns more easily. But in order to do the same thing with the wide network, then we need exponentially many nodes. That's the problem. So in this slide, what I want to say is that in the deep learning world, questions are not about correctness. Which one is right and which one is wrong? That's not the question in deep learning. The more important thing is which one is more efficient. Okay, that should be our question in deep learning. So even with the one hidden layer in neural network, we can approximate any functions. Theoretically, that's possible. But practically, that's not possible because it's not efficient. So when we actually design a neural network in deep learning, you have to ask these questions. Which way is more efficient? Okay. So sometimes when we design a neural network in this way or in another way, they will work, but the performance will be different because one network will be more efficient than the other one. Okay, that is important question in deep learning. Okay, so the idea is simple. So we can actually stack a lot of layers to have a bigger network for a more complicated problem. But why was it so hard? So the idea was actually discussed long time ago in 1980 something. They talked about this stacking many layers. But until 2006 or so, we couldn't have any deep networks. Then why was it so hard? So the problem is in the backpropagation. So backpropagation may not work well with deep networks because there is a vanishing gradient problem. Okay, so that the lower layers may not learn much about the task. So think about this one. These are input and these are output. And from this output, let's say we are working on the supervised problem. So we have labels here. And based on this error, the error information goes down like this. Okay. But this error information vanishes as we go down. Why is that? If you look at these neural network equations, then there is a derivative of this activation function. When we go back to this input layer, every layer we have this term. Okay, and if it is a hyperbolic tangent, then whenever the input is around here or here, the derivative is 0. So every time we multiply 0, then the information vanishes. Okay, so there was a big problem. Even when these higher layers are updated enough, but the lower layers are not updated enough. So we just updated the higher layers and the lower layers are not updated enough, so it got stuck. So Jeff Hinton thought at the beginning of this deep learning era, maybe we can have a good initialization. Then we can solve this problem. So this was the first idea, pre-training. Instead of training this deep network directly with backpropagation, we can actually train the layers layer by layer with unsupervised learning, something like a PCA, but actually they used a restricted Boltzmann machine. They didn't use PCA, okay, but I think you understand the PCA, so let me explain this layer-wise unsupervised learning with PCA. With this input data, then we can train the PCA, right? So we have a PCA. So now we can have hidden a representation, and then we can apply nonlinear function, and then we can apply the PCA one more time. Then we can have another representation, and then we can apply the PCA one more time. Okay. Then we have a weight 1 and weight 2 and weight 3. So these weights are pretty good weights because these weights are reflecting the data regularity or data structure. Okay, so these are not random. Okay, these ones are good. And then we can combine these layers like this. And then we can actually use the backpropagation. So even though we update this layer slightly, but still these parameters are pretty good before this fine tuning. So even with just a little update, then this can improve the performance a lot. So this is the first idea to have deep networks. And then we can actually interpret this pre-training as an optimization techniques and also regularization technique. So this one is a good initialization for these layers. So which means we can understand this one as an optimization trick, right? But also this pre-training is about the prior knowledge. Before fine-tuning, we have something. So that is a prior knowledge. So in the regularization chapter, we talked about this issue, right? So when we have a prior knowledge, and that is actually regularization. So we can interpret this pre-training as optimization or regularization. Okay. So before pre-training, this one is initial point, and when we train with the backpropagation, then probably it will go to the local optimal. Then that's it. But after pre-training, we have a really nice initial point, and then from this initial point, if we minimize, then pretty good local optimal. Also, as I said, since we can interpret the pre-training as a regularization, then how about another regularization techniques? So we can think of dropout, we can think of sparseness. Sparseness can be achieved based on the model structure, model architecture, like a CNN. Or we can have another kind of regularizer. Or activation function can actually encourage the sparse representation, which is another regularization. And also, as in LSTM, we can control the flow with many gates. So since we can interpret pre-training as regularization, so we can apply another regularization, then we don't need pre-training. So in the beginning of this deep learning era, we used pre-training, and many people believe that the pre-training is crucial and is necessary. But since we have other many nice regularizers, sometimes we don't need the pre-training. So now pre-training is not necessary process. Sometimes we use, but most of the time we don't use pre-training.